today, lesson 11, we're going to talk about domain and range. So it's going to relate to the previous lesson we had about relations and functions. So let's go over what domain and range means. So essentially, a domain and range is just a collection of all the possible x values and y values. So the domain means the x values and range means the y values. And for domain and range, the way we express it is usually using set notations. So I believe we learned that in the second lesson, but we can kind of do a quick example of what set notation is.
Yeah, so I can explain this part, I guess. So
Okay.
in your set notation, we first start off with a curly bracket, and then we list the variable that we're describing. So in this case, we can do x for range. And then we would put a vertical slash, and after the slash, we'll put in conditions. So for example, x is an integer, and x is smaller than 10. And then we would end it off with another closing bracket. So what this means is that x can be any value ranging from negative infinity all the way to 9. 8, 9. So in the graph, what this will look like is something like this, where they're just an x value for every single integer. Okay. For your range, it would be a similar notation. So we would start with a bracket. Then we would have the variable y, because we're describing y in this case. And then a vertical slash and conditions. So maybe y is greater or equal to 0. So what this look like on a graph is a graph with all y values greater or equal to 0. So maybe something like this. Okay, so David, do you want to do some examples?
Yeah, sure. We can start off with like a really basic one, y equals x. So if we draw it out, okay. Yep, if we draw out the graph, we can see that it's essentially just a diagonal line straight up and down, not straight up and down. But we can see that the domain and range is all possible values. So y increases infinitely and y increases infinitely and decreases infinitely, and x increases and decreases infinitely as well. So to express this, we would say that the domain is equal to x, where x is the element of the real numbers. And similarly, y, the range will be y, where y is the element of the real numbers. So that will be the range and domain of this function.
Yeah, so basically it can be anything it wants, any number in the world.
Yes, we can also have another one where it's y is equal to 1 over x. This one's going to look a little more interesting. So here we can see that the range does increase and decrease. Well, the domain and range kind of increase and decrease infinitely. But here we also notice that x isn't 0 and y isn't 0 as well.
Yeah, so okay, sorry.
Oh, no, you can go.
Okay, so for x equals 0, we can see that both sides approaches x equals 0, but that never happens when it goes down to infinity. So as the right side goes up to infinity, it gets close to 0, but it never touches 0, and same as the left side. So do you want to describe like the notation we use?
Yep. Okay, so domain, we do the set notation again, and here we say that x where x is the element of the reals, but x can't equal 0. So x does not equal 0, and that will be the domain. And for the range, it will be y, where y is the element of the reals, but y is not 0.
Yeah.
Should we try another one?
Yeah.
Okay, we can have a random parabola, I guess, y equals x squared.
Sure. Y equals x squared. Maybe like +3 or something.
Yeah, sure.
Okay.
So here we can see that the two arms of the parabola extends infinitely in the x directions, but here we notice that there isn't any y values below the y level 3. So so the domain is x, where x is the element of the reals. But here, for the range, it would be y, where y is the element of the reals, but y is greater or equal to 3. Because there isn't any y values below 3, so we just put that there. It's a restriction on the domain and range. So
Yeah.
should we move on to the next topic?
We can do like square root of x.
Oh yeah, that also works. Just show all the graphs,
Yes.
all the possibilities.
Maybe like x minus 2 plus 3 or something.
Yeah, that works.
Okay.
So here we can see that there's a restriction on both domain and range. So for domain, we see that x value is every value. So x is the element of the reals, but x is greater or equal to 2. And for the range, it is y, where y is the element of the reals, and y is greater or equal to 3. So from this, we can also kind of see there's some kind of relationship between some of the parameters in the function and the domain and range. We can see that x is greater or equal to 2, and there's a -2 in the function, and y is greater or equal to 3, and there's a +3 in the function.
Yeah. So what David's talking about is like graph transformation, which I think he'll learn in grade 11. So what this -2 essentially means is moving the graph right from the origin 2 spaces. And then we have a +3 here, which means moving it up 3 spaces. So essentially, it's about transforming a graph or translating a graph. But we won't get into too much details on that.
Okay, so let's move on to some restrictions on domain and range. So we already kind of saw some of them, but we're going to go into more detail. So there are like 3 primary ways that domain gets restricted. So the first way is where the x variable changes a denominator in a fraction, and we can't make the denominator 0. So for example, y over x. So like y equals y 1 over x. We can't have x be 0, so that's a restriction on the domain. And the second way is when we have a square root, so a radical. And the radicand can't be less than 0 because we don't want imaginary numbers. So for example, the y equals square root of x can't be any negative numbers. And the third way is through context of the question. So for example, if the question is asking you something about apples, you obviously don't want the domain to be negative because you can't buy negative apples. This one's not as concrete as some of the other ones, but yeah, common sense, that's one way to put it.
Yes.
Yep, so we can look at an example of the first restriction, so denominator. We can have, for example, the function y is equal to x plus 3 over x plus 2. x plus 2. So we don't have to draw this one out. We can kind of analyze it using the function itself. So here we know that the first x doesn't really get affected. The first x can be any value. It doesn't have any restrictions. But the second x is in a denominator. And we know that the denominator can't be equal to 0. So we can see that x can't be equal to -2 because once x is equal to -2, -2 plus 2, and that gives us 0. So here the domain is x, where x is the element of the reals, and x cannot be equal to -2. And from this, we can also kind of get the restriction on the range, if we want to talk about that.
Sure.
Okay, so we can kind of know the value where we can't have a y. So one way to do this, actually, is there a really good way to do this? Totally forgot.
Yeah, I think for this one, the range is a bit more tricky, so we'll just stick to domains.
Okay, yeah, we'll stick to domain.
Yeah.
Okay, so let's actually talk about radicals now. Should we talk one more about fractions or no?
We could do one more fraction.
Okay, so we can have like y is equal to 3 over 2x plus 5. Just a weird one. So here we know that x is in the denominator, so it can't equal to 0. And one way to do this is that we can turn the denominator into an equation. So we could say 2x plus 5 is equal to 0. Oh, that also works, yes. And we can isolate x, and we find that to make the denominator 0, we need -5 over 2. So that's a restriction. So for the domain, we have x where x is the element of the reals, and x cannot be equal to -5 over 2.
Yep. And for the first one, we can do something like x plus 2 is not equal to 0. So x is not -2. Now let's go to radicals.
Yes, okay. So for example, we could start out with the equation y is equal to square root of x plus 2. So we know that the radicand can't be a negative number, so x plus 2 must be greater or equal to 0, and x must be greater or equal to -2. So that's the domain. So for the domain, we have,
Okay. I thought you were gonna talk more about like the radical.
Oh no.
Okay.
Domain x where x is an element of the reals, and x is greater or equal to -2.
Should we talk about the range as well for this one?
Yep, we can.
Okay.
Wait, do you want to talk about it though?
Oh yeah, sure.
Okay.
So for the range, the graph could actually be any number that's positive, because in the case we have a square root of x plus 2, we're only talking about the principal root, which means that it's always positive. So in this case, the square root of x plus 2 will always be positive. So what I mean by the principal square root is that we know that, for example, 2 squared equals 4, but -2 squared also equals to 4. However, when we're taking the square root of 4, we're only dealing with a positive number. So in this case, we're dealing with 2 and not -2. So which makes the range any y value that's greater or equal to 0. Okay, should we do another example?
Yep, sure. We can have y is equal to square root of 2x plus 2. Do we want to have an outside constant?
Sure.
Okay, we have a plus 3. So again, like the previous one, we set up an equation and we isolate the x. So we find that must be greater or equal to -1. And for the domain, we have Yeah, for the domain, we have x, where x is the element of the reals, and x is greater or equal to -1. And for the domain, it's, how do I describe this? It's shifted up by 3. So instead of having y is greater or equal to 0, what we have is y is greater or equal to 3.
Yeah. You can also describe it like, you can see this function like two components. The first component is the radical, and the second component is the number 3. For the first component, the smallest number it could be is 0. And for the second number, obviously it's always 3. So the smallest overall would also be 3, because 0 plus 3 is 3. But yeah, just like what David said, it's y is a element of the reals and y is greater or equal to 3. Okay.
Yep. Okay, so let's talk about the last type of restriction, which is common sense or the context of the question. So we might have a problem asking that if one apple costs $2, what is the domain of the function that relates the number of apples with the total cost? So cost of an apple is equal to 2 times the number of apples we have. So here, we have a domain where the x can't be any negative numbers because we can't have negative apples. And this also means that the range will be also positive. So y is, oh yeah, the element of the reals. Oh, no, not the reals, the integers.
Yeah.
Yes.
We could also just write like whole numbers, but this
Yeah. Yeah, we can't have like part of an apple. So it has to be either a whole apple or no apple.
Yeah. So for the range,
we also can't have negative dollars. And if we buy no apples, it will mean we have 0 cost. So y also has to be greater or equal to 0. And y,
oh, sorry. 2, y is divisible by 2. Because every apple costs $2, so the cost can only be a multiple of 2.
yeah, oh yeah, that's true.
Yeah. This just means y divided by 2 is an integer. Or like 2 divides y. Okay, should we do another example?
Oh, we can.
Okay.
So, okay, let me think of this. Huh. Not a really good word problem maker.
Oh, okay, I can make one.
Oh, okay, thank you.
Yeah, so like maybe cost of pears is $1 each.
Oh yeah, that works.
Or like pears is like 3 each. Do you want to like talk about domains or should I do it?
Yeah, I can do it.
Okay.
So like the apple one, we can't have negative pairs. So the minimum we can have is 0. So x is greater or equal to 0 and an integer. And for the range, like the apples, we can't have negative dollars. So y has to be greater or equal to 0. And this time it's $3 per pair. So y is divisible by 3.
Yep. What's up next?
So we have function notation.
Oh, okay.
Yeah.
Right, let's do it.
So previously we kind of expressed a function as y equals something x plus something something. So that's the previous way to do it, but there's another notation we can use. Yeah, for example, this is a function we can express. But there's another function. Instead of using y, what we instead use is f of x. So f bracket x.
Oh yeah, very important. F of x can only be used for functions. So if you remember from our last lesson, a function is where one x shapes to only maps to only one y. If you use this for a relationship, then you're using it wrong. For a relationship, use y equals, and for a function where one x maps to strictly one y, you can use f of x.
Yeah, you wouldn't use f of x in like an equation for a circle.
Yeah, exactly. So for f of x, I find a lot of people like are confused about it. So how I like to describe it is you're taking an x value, you're putting it into this sort of machine. Pretend that there's a machine here, and the machine is called f of x. And then what you get out of it is you get a y value. So in a sense, you're taking an x, you're putting it through f of x, and that maps out to a y variable. Which is why the notation is f bracket x. So for example, if we have f of x is equal to 2x plus 5, then we have what x such as 1. We plug it into this machine. We substitute the 1 into the x, so 2 times 1 plus 5, and then we get out of 7. So in other words, f of 1 is equal to 7. But essentially what you're doing is you're just plugging in this x into this x. If that makes any sense. David, do you want to explain it a bit?
I think you explained it pretty well, but if we to solve an f of x function, what we do is that we put a number into f of x, and then we just basically look at all the places where x appear. Like no matter where they appear, we replace it with the number we just inputted.
Yeah, so you want to give like a specific number example?
Yeah, we can have the number 13.
Sure.
So we look into the other side of the equation sign, and we basically just spot out all the places where x appear, and we just replace it with 13.
Yeah, so that's 31, I believe.
Yes.
Maybe we could do like a harder example, like f of x is equal to 3x cubed plus the square root of x minus 2.
Sure.
Okay, maybe we could
So
do like, I don't know, you choose.
3, for example.
Okay.
So again, we just look at where all the places where x appear, and we just put the number we have in there. All the places where x appear, and remember to bracket the number, so just in case you have a negative as an input. So what we do now is that we just solve it. So 3 times, oh gosh.
81 plus
Oh, you're
1.
fast. Okay. 82. Ooh.
Yeah, so just think of it like a machine kind of thing, right? You're putting in an x value, and then you're substituting x to the places where x is used, and then you get out of a y variable.
Yeah. And do you know that even though we say f of x, the f can technically be any other letter. We can have something like g of x, h of x.
Yeah. So like anything you want, g of x, or it's usually like f of x, and then for the second function, you do g of x, and then for the third function, you do h of x. But like in the example up here, cost of apples is equal to 2 times the number of apples. I actually also used a function notation. So in this case, the cost of the number of apples is equal to 2 times the number of apples. So in this case, cost is like the letter F. Apples is like the letter X equals 2 times X, if that makes sense. Okay. Should we give like more examples?
Sure. We can have f of x. Oh, f of x is equal to x squared plus 4x plus 4. Not sure if it's harder, but here, do you want to choose a random number?
Like 0.
Sure, that works. So if we input 0 as x, we replace all the x's. So we have 0 squared plus 4 times 0 plus 4. And that just gives us 4.
Yeah. So really, a function is not like the functional notation, just think of it as y, right? I can also write this as y is equal to x squared plus 4x plus 4. They're essentially the same thing. Okay, should we give like a function and then we give the value of y and they have to figure out the value of x?
Sure.
Okay,
Do you have a specific function in mind?
you can choose one.
Oh, okay. We get f of x is equal to x squared. Wait, 2x squared.
Wait, I don't think they've learned quadratics yet. Just give a linear one.
Oh, okay. We can do 5x plus 16.
Okay. And then what is f of x? Like the
What f?
value of y.
Oh, let me think of it for a while. f of x is equal to 32. I don't
32?
think that will go out nice, but
Yeah, it won't go out nice. Let's do like
35.
35.
Do you want it? Do you have another number that works better?
I think 37.
Oh, okay. Yeah, we can try
Wait,
that.
no, I mean, sorry, 36.
36, okay.
Yeah. So find out what x is, and you can type your answer into the chat. Oh, 4. Yeah,
Yes, Patrick.
good job. So we will just take this expression over here, and we would equate that to 36. So 5x is 20, and x is 4. And so if we were to write it as a pair of coordinates, we would write it as 4 comma 36. Pretty sure that's the end of the lesson.